So can you record? Okay, thanks.
32
22.
is ahead.
No,
This one.
22.
22.
Yeah.
Okay.
In rule number 3, the 8 is means we shift the FF to the right, is it?
Which one?
Row number 3, in the table, row number 3.
This one. Or this one. This is three or four.
Number 2, this one.
Okay.
The 8 is means we shift the FF to the right, is it?
Yeah.
So,
Only rotate right. It's not shift, it's
How?
actually rotate.
okay, how if we want to rotate to the left? Is it possible?
Cannot. You rotate right, but many times.
Oh, okay.
So let's say I want to make it 0, 0, 0 like that. FF 0, right? Okay. It looks like I rotate left by 4, right?
Yep.
But you can also do it by rotate right 28 times. Okay, you can do it by, if you shift it 28 times, it's still the same.
Yeah, true.
So there will be 28.
Okay, thanks.
So no problem, can be done. All right, so let's resume. Let's go to the new topic, general data processing instructions. Okay, so for this section, we will cover by batches. Okay, so the first batch or the first group of data processing instruction covers the arithmetic instructions. We have 6, namely add with carry, add, reverse subtract with carry, subtract with carry, and subtract. I see a typo actually. This one should be SPC. So I think for the add, we all know lah. For if you have taken microprocessor before, add is add. But for the subtract, you have to be careful. There may be some surprises here. Okay. So for the add and add carry, I think it's straightforward, just like any other microprocessor. And then the other one is the other thing we have to know is add is commutative. You can add A plus B or B plus A, the result will be the same. But for subtract, you cannot do that. Okay, so that's why there is instruction here called reverse subtract. Okay, so you can have normal subtract and reverse subtract. Another thing here, we have to be careful when you do subtract with carry, is that the carry is inverted. Okay, the bit in the carry is inverted. So if you add 1 in the carry, means there is a carry, but if you subtract, then 1 or the other way we look at it is that 1 means normal, not normal. 0 after subtract is normal. But when you subtract, 1 after the subtract is normal, 0 is not normal. Okay, so I think we've seen this before, right? When we add too many numbers and there's an overflow, you have to detect the overflow or the carry. So for example, if you see the example of the clock, okay, for example, 3 hours from 11 will become 2 o'clock because it overflows at 12. So same with 8-bit numbers, the limit is 255. If you take 224 and add 64, you'll get 32. Same thing if you go backward, 32 minus 64, you get plus 224. So you do have to know the limits of the number range, and actually one more thing is that you have to know whether the number is signed or unsigned. Okay, so 4 things to remember. When you subtract 2 n bits, you get n plus 1 bits. So if you have 8 bit plus 8 bit, your answer must be, you must prepare a 9-bit sum to to ensure you catch everything. That is for addition. If you multiply, if you have 8 bit times 8 bits, you need to have 16-bit product to make sure you don't miss anything. So that's what we mean by these two lines here. So after that, then you have to worry about overflow, because if you have 8 bits and 8 bits that's too big, then you have an overflow. So how do you detect the overflow? So if you have unsigned number, you will look at the carry bit. But if you have signed number, you look at the overflow bit and not the other one. Okay, so if you are doing sign, for example, you only look at the overflow, not the carry bit, because the carry bit will be meaningless while you're doing arithmetic with signed numbers. So also you have to be careful about converting types. Okay, sometimes you have to combine unsigned number with signed number. You have to convert one or the other. So you have to know about that. We have done that in C. Same thing applies in assembler. All right. After you do your add, subtract, whatever, the results will be in the processor status register. We have the NZCV bits. Okay, so N means the result is negative, very easy. Okay, just look at the most significant bit. Okay, so most of the time this will be bit number 31. Okay, it's the same thing as bit number 31. Z means the result is 0. Okay, if it's 1 means the result is 0. So if you like your logic gates, this is just the NOR gate. Okay, if all the inputs are 0, output will be 1. Okay, this is your NOR gate. But the bits will come from bit 0 to all the way to bit 31. Okay, so it's a 32 input NOR gate. Then we have the carry. Okay, so for unsigned add, 1 means the result has carry. So this one also not too difficult. Okay, for example, I have make it very small. Okay, make it one number. It's only 4 bits. Let's say I have this number 8 plus 7. Okay, no carry lah, because 8 plus 7 is 15, and 15 is still within the range of a 4-bit number. So carry is 0. But you add one more, okay, 8 plus 8, I will get 16, and 16 is too big for 4 bits, so carry will be 1. So same idea goes for 32 bits. So I think for unsigned numbers, this is quite straightforward. Just a refresher. When you do subtract, 0 means result has borrow. Okay? So this 0, okay, go back a little bit. Okay, 1 means there's a carry. So carry is not normal. No carry is good. On subtract, borrow is a problem, and no borrow is okay. So that means when you do subtract, a carry flag of 1 is good. Carry of flag 0 means you need to do something about it. Okay, so that is for add and subtract. And then for the shifts, the carry bit carries or maintains the bits being shifted. And we will have later, we will have shift instructions. Okay, for example, we have shift right, for example, arithmetic shift right, like that. So the last bit shifted out will be in the carry bit. So this bit 0, for example, will be pushed to the carry bit. So you can detect the last bit being carried, being in the least significant bit before it's being shifted out. And lastly, we have the overflow bit, where this is only meaningful for signed numbers. Okay, I don't have the complete details. This is already in shortened form. Okay, so if you are doing unsigned addition, carry flag of 0 means the result is correct. Okay, so you want a carry bit of 0 after you do unsigned addition. If you doing unsigned subtraction, you want a carry flag of 1. Okay. If you're doing addition, carry flag of 1 is something that you don't want. That means the result is incorrect. Same thing with unsigned subtraction. Carry of flag of 0 is no good. So if nothing else, if you can do the correction of the result, okay, but maybe you just want to throw away the result because the result is not correct. Okay, so for overflow, if the overflow is 0, that means the result is correct. Okay, so what do we mean by result is correct for overflow or for signed number? Okay, so for some signed number is like this. Okay, for example, I have number 7. I add 1 in 4 bits. Okay, I will get 8. So 7 or plus 7 plus 1, I get minus 8. Because in signed numbers, 1 here means negative. So what we see the condition here is what we see here is a condition where positive plus positive gives you a negative number. So this is an overflow, and it is because you don't have enough bits. So if you enlarge the word size to 8 bits, the problem will be solved. But for right now, this is no good. So for sign addition, okay, so if you have, let's say this is operand 1, operand number 2, and this is the result. Results, okay. So if it's positive plus positive, the result is positive, which is okay. For example, I have 6 plus 1. The answer is 7. 7 is still within the range. So I get positive plus positive, I get positive. But if I have positive plus positive, answer is negative. Just like I showed you just now, it's no good. Also, you can have an incorrect result when you have negative and negative giving you positive. Okay, this is no good. And then we have negative, of course lah, this is the one that we expect, negative plus negative, getting negative, this is okay. And lastly, let's complete the table. If you're positive plus negative, you can never have overflow, and negative plus positive always okay. So the condition happens, okay, for overflow, the condition happens only when you have the same sign for the operands and the sign changes after you perform the addition. If so, when you have this, you have v equal to 1. Okay. Okay, so maybe another way to put it is same sign getting you the operands are the same sign operands, but different sign results. Okay, so for sign addition, that's the rule, and for sign subtraction, we reverse it. Okay, so for sign subtraction, positive minus negative or negative minus positive is the one that will give you the overflow. If the signs are the same and you do subtraction, you will never get overflow. So that is out of the scope. You can try to find your own combinations lah. But just like here, the carry bit is reversed. For sign subtraction, the condition for getting the overflow is also reversed. Okay, cannot stay too long there because there's a lot more instructions to cover. All right, and then the next group is the logical. So we have AND instruction, we have OR, and we have EOR, and then we have BIC. And I seem to recall there's also another instruction called ORN, or not. This one, better check. I think is in the updated version of the ARM. Okay. For this one is AND not. We have also OR not. Okay, so AND, OR, and exclusive OR, we all know. Okay. For example, I have this number. Okay. 1010 1100. Okay. For all these combinations. So if it's AND, then we just AND lah. So 1 AND with 1, we get 1, and then the others I get 0. Okay. If I do OR, then any column is 1, I put 1. Any column, all column 0, then I get 0. If it's exclusive OR, we will see if the same. Okay, if the number is the same, we get 0. If not same, we put 1. Okay, so sometimes it's called the equality. Equality. Okay, so 1 when equal, 0 when not equal. Actually, not equality lah. Okay? The equality is actually exclusive NOR. Okay, now this new thing called BIC. This is AND NOT. Okay, what happens? Okay, so what happened is we AND with not AND. So we have to reverse the bottom, the mask, and then we do the AND. So to complete this, we reverse everything, toggle everything, and then we do the AND. So the answer will be 0, 0, 1, 0. Okay, so we have to not. Okay, we not this, not the mask. So we get the modified mask. Then we do the AND. Okay, so this is the normal AND. This is the AND with the inverted mask. So why is it called bit clear? Is because when there's a 1, you clear the bit. When there's a 0, you don't clear. So if you look at the mask, when there's a 1, you clear. So that means where the column has a 1 there, you definitely clear. So here you clear because you have 1 there. And when the 0, you copy. So on top here, we have 1, 0. So for the bottom, we copy. Just put 1, 0 there. So there is bit clear, and the new instruction available on some models of Cortex. I'm not sure whether it's on the Cortex M4 or AND, okay, or not. So it will be like this lah. It will be like the OR, but invert the mask. I don't put it here because I don't see too many examples of it. Not sure if it works, but it's in the instruction set. Okay, so something you can play around later if you have time. Now we are halfway through the notes, 3:30. Maybe later we come back to this page lah. All right, and then here we have the barrel shifter stuff. Okay, remember that operand 2 goes through what's called the barrel shifter, and the barrel shifter can do 6 types of operations. 5. Okay, 5. But the second one has 2 variations. Okay, so number 1 is LSR, or logical shift right. Logical shift right. So L is logical, and if you see A is arithmetic, and then SR is just shift right or shift left. Okay, so when you see LSR, we always put in 0 from the left. Always 0. Okay. Same thing here. When you have the keyword logical, we put 0 to the other side. So if you do logical shift right 4 bits, so all the bits will be shifted to the right 4 times, and 0 will be shifted in to the left. And the last bit ejected will be in carry lah. So in this case, the carry will be this one. So carry will be 1 also. If you do logical shift left, we'll shift in 0 from the right, and the carry will take the last bit. Okay, the last bit that was just before getting killed. So here, course, these numbers are all ones there. So carry will be 1. Okay, so anytime you see logical, you can think of it as unsigned number. So LSR is actually equivalent to shift right in C and is for unsigned. Okay, so shift right is unsigned division, shift left is unsigned multiplication. There is no such thing as okay, this is unsigned division and unsigned multiplication. Okay, when you go down there, you can see this is for sign and then it's only sign division and there's no such thing as sign multiplication because they're the same. Okay, for these examples, for arithmetic shift, the sign bit is rotated. Okay, so to solve the bit on the left, you have to feed back the sign bit. So for this example, okay, if it's positive value, you want to maintain positive value because when you do sign division, you want to keep the sign the same. Let's see what is the value here. 1111 in hex. I'll check my calculator. Yeah, this value is 61440 in decimal. If I shift 4 times to the right, that will be like shifting. That will be like dividing by 16. So I will get 3840. Okay, if you convert this in binary, it will be 38. Convert this binary to decimal will be 3840. So this value 3840 times 16 will give you back 61,440. Okay, so one position to the right will divide by 2. 4 positions will divide by 4 by 2 to the power 4. So one position divides by 2. So n position will divide by 2 power n. Okay, so that's why you have this number lah. Okay, sign division by 2 power n. Okay, so for the bottom one, we have 1 at the back there. Okay, so that makes it complex. That will make it sign number. So let's try to calculate this. Can my calculator do this? Don't think so.
Which one you're trying to do? ASR.
Yeah, ASR. What is the value in decimal?
Okay, so actually Windows calculator got ASR.
Oh, okay.
You can try if you open Windows calculator under programmer. There's a bit shift. There's an ASR. Open calculator.
Yeah, let's try that.
Calculator. Okay, that one. And then you go to that triple burger on the left side, upper left side, and then change to programmer mode.
Okay.
And then down there, there's a bit shift.
Okay.
You can click that
So
bit shift and select the kind of bit shift you want.
okay. So
But you have
first
to
enter
put some
hex first
value
lah.
first lah.
Yeah. So this one will be 800 F000, right? Then we shift arithmetic shift. Yeah. Arithmetic shift. Yeah. Okay. Let's do it 4 times. Shift. Nope.
And then when you press that, you have to type how many shifts you want.
How many? Yeah. So
okay, equal. Yeah.
yeah, but I want to convert it to decimal. I still want to convert this.
Click
Okay,
deck. Click deck.
Wait. I have to shift I have to shift back left for reset it to the original value. Okay, and then convert to deck. And then how to make it signed number. It's not signed.
No, because currently you're keyword, so it's actually 64-bit number.
Oh,
Or you can click the keyword and
Okay.
select a double word.
Okay, that one. Okay.
That's double word lah.
Okay. So this is the one I want. Okay. Now I just shift this 4 times. Just want to show that why this is doing this sign. So when you shift it once to the right, you will divide it divide by 2. So it becomes minus 1 billion. Okay. Shift again by 1, it becomes minus 500. Shift again by 1, minus something. Okay. So let me see. One more. Okay, one more. Okay. So this pattern, this binary pattern will be the same as the one shown here lah. Okay. So the point is, if the number is negative, you shift it to the right, it will become smaller negative number. So just now it was minus 2 billion, now it becomes minus 134 million. So that's all lah. That's all I want to show. So if you do ASR and the number is signed, then it becomes a smaller negative number. So that's why you choose ASR is because it's a signed number. Okay. Enough lah. And then we have also rotate. Okay, rotate just means that you swap the bits. Okay, let's rotate this 4 times. Clear first. Okay, so 8000 F005. Okay, and then we rotate this number 4 times. Okay, so if you rotate, circle the shift. Okay, rotate means the number from the right goes back to the left. So here you can see 1 here and 1 to the left and 1 to the right. So if we rotate once, we'll see 1 1 on the left, and then see this 0 on the right side is 0. So the 0 will be rotated to the left. So I will get 0 1 1, and then if I do one more, I will get the same. Why do I get the same? Only 3 times, one more. Okay, so now after 4 rotates, I get the same number as the one on the screen. So 58000 F00. Okay, same. And then we have another one, rotate through carry, circular shift. Okay, so this one is the RRX. Okay, so it's good that the Windows calculator is doing exactly, is providing exactly all that is available on the ARM. So rotate through carry means that you have to declare the carry. I don't know where is the carry here. Doesn't matter lah. Okay, let's just rotate, see what happens. Not sure where the carry is. Looks like the carry is 1. But now instead of only 32-bit, it becomes 33-bit. Okay, so normal rotate is 32-bit, and you can rotate left. Okay, here is rotate right. You can only rotate right. You cannot rotate left. If you want to rotate left 1, you just rotate right 31 times. That's how it works. But RRX means that you have a 32-bit register plus the carry, and then it feedback like that. You can put the carry on the left or on the right. It doesn't matter. Okay. Oops. Okay, you can do it this way. Still goes through the carry bit. It's the same. Okay, so that's what we mean by RRX. So the rotate through carry can only be done once. All the other rotates and shifts can be done many number of times. You can rotate 1, time, once, twice, 4 times, 10 times, no problem. But RRX, you can only do it once. Okay, any questions? Okay, you're all excited.
So,
Yeah.
If today we have the ROR, then the number is 8, means the 000000101 will be bring to in front, right? Means the bit 0 to the bit 7 will be bring to in front, is it?
Which one are you? You're referring to
ROR,
this
ROR.
this one?
Yeah.
Okay. Okay. So
So if today we got the number is 8 instead of 4.
where? Oh, this
So-
one. Okay.
Yeah.
Okay.
Yeah,
So you just take this number and shift again, rotate again. So that everything will be moved to the right one, 4 more bits. So okay, so the answer will be this 0101 will shift 4 bits. So I will get 0101 here, 1000 here will go here. This 12 times 0C will be here, and then 111 here. 000 here, and then this 0 will be here, but it will be on one step lah. You will do it in one step.
Okay, thank you, sir.
And the barrel shifter is powerful. They can do all this free, no clock cycles, and no delay. Okay. If you're using a normal shifter, maybe one step is 1 clock. Here, even if you rotate 31 times, it doesn't take any clock cycles. Okay, so this one is a potential exam question. And you can see that actually when you do ASR like this, it's actually a synonym. Okay, so move, for move you have a destination register and a source register, but here the source register is being shifted through the barrel shifter. So you can write it this way, or you can just write it ASR. So basically the ASR and the LSR instruction, they are not part of the language or the machine language. It's synthesized. Okay, because for example here, the add, you can have this add, and you can have the LSL there on the right. Okay lah, might as well do it lah, one by one. Okay, what's this answer? This number is no good lah. I think this number is too complex. Not too bad. Okay, so up 0, this number, logical shift left 1 bit. So I will get 11110. If I shift 1 bit to the left, I will get 0111 1000. Okay, so here the answer will be 787878 like that. Or if we do it in binary, okay, we want it in binary, right? So it will be like 0111 1000 4 times. Okay, one more, and so on. You get the idea. Enough space. Okay. Or just 7878. Okay. That is because we shift by 1 to the right. And then for number 2, R1.
So this is shift left, isn't it?
Yeah. What a waste of time. Shift left. Yeah. Alice. Okay. Let's just do the hex thing lah. Okay. So if I have this first, okay. If I shift left, I will get the first neighbor. I will get 1110, and then I will get 0001. and just repeat that lah. So this one will become E1, 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 E1. Okay, this pattern will be repeated 4 times. Okay, and then if you do LSR, but this number is different now. Okay, so it's just 5. Okay, so 5 is 0, 1, 0, 1. If you shift it right, I will throw away that 1 and I will get 2. So it's just 2 lah. Okay, so this is a lot of zeros here. Then at the end we have 1, 0, 1. If shift it to the right, I will throw away this 1 and I will end up with 1, 0 at the last as the last 2 bits. Okay, so ASR. Okay, so we have AA here. AA is 1, 0, 1, 0, 1, 0, 1, 0, 4 times. Okay, and if I shift to the right 2 bits, I will put in 1, 1 twice, and then all the bits will be shifted. So the first nibble will be different, then the rest will be the same up to this point, and then here I will have 0, 0. Okay, so the answer will be E A 8. Zero, zero, zero. Okay, so actually these 3 are tough, and then the number 4 is quite easy because here we just rotate 16 times. So this number, if you rotate 16 times, it's just the same number. Okay, what's even more evil is if you rotate 32 times, it's exactly the same number. But here, if we rotate 16 times, that means the lower part gets swapped with the top part, but they happen to be the same. So you get the same number there. And this is a trick, okay? So here we have R2 shift left by 1. So that means R2 times 2. Okay, R2 times 2 plus R2. So you actually get 3R2. Okay, this is a way to do multiplication without using the multiplication instruction. So R2 shift left by 1 will give you 2R2. You add this number with the original R2, you get 3R2. So if but this number is no good lah. Let's change this to R1. Make it smaller. So R1 is 5. So the output will be 3R1 or 3 times 5, so just 15. So your answer, your final result will be F, whatever the value. So I don't have to do any shifting actually. Okay, by analyzing what it's trying to do, you know that it's trying to multiply by 3. So if the original number is 5, 5 times 3 is 15, they'll put the 0F. Okay, no need to do any shifting for this one because we know it's doing mathematics. Okay, same here. Shift right by 1, so 5 divided by 2.
Sorry, on the one. For the number 4 isn't the one is R1 the example that you give us is R0.
Which one?
The MOV R1 RR.
Yeah. Yeah, always time to screw up. Clear everything. R1 okay, R1 rotate 16 times. Okay, yeah.
Why did you change R1? You just changed the instruction to R0, settle.
Yeah lah, but it's okay lah. Just give another example.
Move R0,
Biarlah.
R0, settle habis. Tak payah tulis.
No, the thing is this R0 same, cannot see the difference.
Yeah.
Yeah. So this one also you can change lah, but let's do an example with something that is visible. So if you rotate 16 times, this bottom nibble, the bottom word will be swapped with the top one. So your answer will be 0005, 0000 lah. Okay, at least something there lah. Okay, so shift right is divided by 2. So instead of 5, we get 2 here. In wait, again, bad source register. R1 is easy because it's 5. This one is too complex. It's good for masking. It's like masking question, but not for number. We want to calculate something, make it easy. Here and the last example, logical shift right. Same thing because answer is also 2. Because you're still shifting by 2 bits, but the number is but we are using logical. See, this is arithmetic. But actually can make it interesting lah. Okay, so if it's F like that, we know it's actually okay F 0. Yeah, this is minus 16. Then if we shift to the right by 1, then we know it's minus 8 and minus 4 and so on lah. Well, anyway, CQI, constant quality improvement, can improve the examples for next time. Okay, so to finish up the bit manipulations, hey doctor, but RRX will only shift 1 bit. Yes, that's what happens. Okay, RRX is the odd one out. It's the only one that is fixed. The others you can specify how many bits you want to shift. All right, so word length extension, we can sign extend or unsigned extend. So here what we're doing is this example. The original is AA, BB, CC, DD, and we do sign extend from byte to word. So the DD is copied, and then the sign bit here, because DD is negative. So what is DD? It is, I think, 1101. Okay. So because the MSB is 1, okay, so it becomes F all the way. If the first bit is 0, then it becomes 0. Next, we can also do 0 extend. So for 0 extend, it doesn't care what is the MSB, even though it's FF. Okay, all zeros, all the way to the left. So for these instructions, the code here is S for sign, U for unsigned, B for byte, and H for half word. And then we have reverse instructions, which is more like trying to help convert big N to small n numbers. So for reverse, REV, they all got swapped. Okay, so here we have lowest byte becomes the highest byte. Second lowest becomes the second highest. Second highest becomes second lowest, and highest byte becomes the lowest byte. And then we have ref 16, where you have same idea, but within is isolated within the half word. And lastly, we have the reverse with sign extend. So almost like the ref 16, but from the sign bit, we sign extend it. So B is 1011. So because this is 1 in binary, so becomes FF on the left. Okay, so I don't know about you, but you do have to be quick lah. So for me, I see B, I already can write 1011. If I see A, I can write 1010. So that one is something you need to do some practice on. If it takes you too much time, then maybe have a table somewhere beside you. And then we have RBit. This is in Cortex M4, not in M3. It's quite a specialized instruction. I don't know about you, but I think if you look at you go stand back at your monitor. Okay, I do this is straight, but for me, if I stand back, I think it's like that. It's curved. It's my illusion. It's an optical illusion. I don't know about you. How about it? Anybody have the problem like me? I think it's curve.
No, not to me.
Your eyes are good.
No, my eyes are worse than yours. I'm wearing spectacles. You are
I'm
not.
also wearing spectacles.
Must be your lens.
Maybe. Okay, so the R bit is they reverse all the bits. Okay, so bit 30, bit 31 becomes bit 1, bit 29 becomes bit 2, and so on. Okay, it's like that. And then we have multiplication. Okay, multiplication. Do I have it in the notes? Yeah. So for multiplication, it was not in the notes last semester. I put it back because seems to be a lot of use for it. Okay. We were trying to make it simple, but too simple is also bad. Okay. So multiplication is a complex instruction because there can be up to 4 operands. Okay, especially for the MLA version. For the multiply only, we have destination register and then 2 source registers. Okay, so that one almost like the normal instruction like add, subtract. Okay, but the operands, I believe it's 16-bit only. Okay, so it doesn't use the whole 32-bit. So this thing I think is 16-bit and becomes 32-bit. Okay, so if you want to do this, be careful. And then we have the long version where you have 32-bit times 32-bit, and the answer is 64-bit in 2 registers. So that is another instruction. But this is the basic one. 16 bits times 16-bit becomes 32. Then we have multiply and accumulate and multiply and subtract. So these 2 instructions, they are useful if you are doing DSP. As for DSP, this is called the MAC. Sometimes it's called the MAC. So we have the multiply, accumulate. Okay, sometimes it's called the MAC operation. So we multiply and then we add to the accumulator. So normally system works like this. We have the accumulator, and then the accumulator fits back like that. And then from here we have the signal. This is the signal, and then we have the gain. Okay, so one of them will become the signal, one become the gain. Okay, so signal times gain, and then you add, and then gets added to the accumulator. This is not correct. That's not the correct diagram, but get the idea lah, more or less. Okay, so if you are going to multiply a big number, you have to use the long version. So here the difference here is there's a L at the end. Okay, you can see in the middle it's the same. We have MLA and MUL, but at the end there's a L. So here we have 32 bits times 32 bits, and then here we have total 64-bit register. And for multiply, you can use any register, but of course for accumulate, you need to have the same register. Okay, but not on the 16-bit version. Okay. Here all can be different. All can be different. Here, RD high and RD low must be the same set of 2 registers. Okay, so for multiplication, there's so many restrictions. So before you use multiplication instruction, read the manual 3 times maybe. Right? So you cannot use stack pointer as any of the registers. You cannot use the program counter, of course. And then if you have the S suffix, then there are extra conditions. So not a very pretty instruction lah. But for normal sequences like this, should be okay. Maybe you can try with the emulator after this. Okay, so take a short break, and while you take your break, you go anywhere. I'll try these instructions on the emulator. Okay, so 10-minute break from now to 4:17. Okay, we have only 1 hour left, or less than that. It should be enough to cover everything.